So thank you for the introduction, Seth. As my name is César Bernabé, and today I will talk about verification pain points. And before I proceed with this presentation, let me already explain what a pain point is, because it's, I would say, a cool term that computer science recently borrowed from marketing, and it basically describes a persistent or recurring problem with, for example, a product or a service, and a persistent or recurrent problem that frequently inconveniences or annoys customers. So in this presentation, I'll then discuss recurring problems that people face when starting verification projects, and I'll also present how we are working towards solving these recurrent problems. So before I actually start, let me first introduce myself. I'm from Vitória. It's the capital of a tiny state in the southeast region of Brazil. I included a picture here so you become a little bit like, I went to visit the city. It's a very nice city. It's cheaper than Rio. So yeah. My background is on computer science, and during my master's, I conducted research on ontologies for software engineering, and then I joined the biosemantics group at Leiden University Medical Center in April 2020 as a PhD candidate. So I'm almost there. Hopefully this year I'll be a doctor, as Seth said. And in July, also 2020, I joined the European Joint Program on Rare Diseases as part of my PhD. I will also talk about this project, this program in this presentation. So I will start this presentation by explaining the research topic and mentioning some relevant challenges that can affect the process of making data fair, that is the verification. Then I will present some recent experiences from our group that allowed us to identify these challenges in verification, and then I will present our contributions towards mitigating some of these verification challenges. So let me start with the research topic, fair verification, and the application of this in rare disease data. Oh yeah, before I dive into the topic, I just want to clarify that I'll be using the words stakeholder and collaborators here interchangeably as a reference to everyone involved in the process of making data fair. So these include researchers, data stewards, developers, and so on and so forth. So as you probably heard before, FAIR is one of the buzzwords of the moment. The FAIR principles provide guidance towards making data findable, accessible, interoperable, and reusable. The principles were developed to potentialize the value of the data and other resources for research and innovation, thus allowing data to be easily discovered, accessed, and reused under clear conditions. Making data fair also requires a great deal of effort from our people involved, our collaborators, but the advantages pay off the investment. As bioinformaticians, we are all aware of the annoying amount of time that we have to spend on reformatting data when we want to run, for example, data integration and analysis. And indeed, some literature says that reformatting and integrating data is a time-consuming process, which can often take up to 80% of the time in any given project. So the main aim of FAIR is to gradually decrease this number by allowing data to be automatically handled by computers with minimal human intervention. So the more fair, or the fairer the data sets become, less time is needed on data integration. So when I was brainstorming some examples to support this affirmation, I also tried to do something that most people have been doing in the past few months when we have a question. We ask AI. So I asked GPT, can you provide me with examples of the benefits of FAIR, most more specifically, use case examples. And I got a very long response with long list of projects, of examples of the real world that use FAIR to accelerate research in several fields. And I promised that I checked each project, and they're all real projects. ChatGPT didn't invent this information. And yeah, you can see here a list that covers research data sharing, healthcare, digital agriculture, cultural heritage, machine learning, and so on and so forth. And I repeated the question, and it generated another list with the new projects. I checked all the projects, they are real. And here I highlight the rare diseases example because it's the project I work for, the European Joint Program on Rare Disease. Rare diseases is a project that uses FAIR to foster research on rare diseases. And in fact, the effective rare diseases research ecosystem that is being developed by AGPRD relies on FAIR to overcome some barriers faced by researchers right now. Some challenges of this research in rare diseases, especially in Europe, are: first, data from patients cannot leave the source due to legal and privacy protection constraints, which is good. We need to protect patient data, but, well, it hinders integration. And second, it is very difficult to integrate data because of its heterogeneity, like language differences, ambiguity of data. Let me give you an illustrative example. So suppose a researcher in the Netherlands wants to find data on rare diseases in other European countries. So where does she start? There is no data catalog, so she will have to, like, for example, contact her colleagues, patient advocates, and hospitals to see if they have the kind of data that she needs, and then asks for permission to access this data, also taking the risk that this permission may be refused, and so on. This can take a lot of time, like between finding the data sets, contacting people, people responding, you get you ask for access. This can take months. But let's say our researcher does not give up, and she persists, and she finds data sets in the Czech Republic and Greece, and gets access to a very tiny excerpt of the data, very tiny part of the data. And then the data looks like this. So now she has to reformat the data, translate it to Dutch or English, taking the risk of, like, getting the translation wrong. She will also have to understand the data to make sure that they're really talking about the very same thing, and so on and so forth. So she hasn't even started her actual research, but she has already lost months in just trying to get access to data and then trying to integrate it. But let's imagine that in another example, she had the data magically made FAIR by our FAIRi. Sorry for the joke. And the FAIRi included the data sets on the AGPRD virtual platform, for example, so our research can quickly find the data. And she also annotated the data with ontological terms. So these terms are agreed upon the rare disease community. And now our research just have to ask the machine to reason over the ontology codes, and the machine will be able to automatically make sense of the data and find human readable terms regardless of the language, and integrate this data, thus saving a lot of time from our researcher. So then you might ask, well, what did this FAIRi do? She transformed the raw data, let's say, into FAIR data through FAIRification, which is the process of making data FAIR. So there are several workflows that define the steps of FAIRification. And the example that is shown here in the screen shows a generic workflow, with 7 steps, and the steps are grouped into 3 phases. So in the pre-verification phase, stakeholders identify the verification objectives and they analyze the data and metadata. In the verification phase, stakeholders define a semantic model for the data and metadata. They make these models linkable and then host this linked data into a FAIR repository. And in the post-verification phase, the FAIR data will be evaluated against the verification objectives. The problem is that transforming data into FAIR data is not like a magic trick done by the FAIRing, but it's actually a lot of work. And depending on the size of the data and the size of the project, the implementation of the FAIR principle can be quite complex. And although the frameworks and the FAIR principles provide guidelines for making data fair, they are implementation agnostic, meaning that they don't describe how each community should make their data fair. This decision was actually made on purpose to make the FAIR principle to actually respect the particularities of different research communities and to give the freedom, let's say, to decide on the best, for these communities to decide on the best implementation tools, standards, and other choices. So the same applies to principles and workflows. The workflows, they define the steps, but they don't provide very detailed guidance for these steps because it was upon the communities to decide how to do so. But this lack of, let's say, guidance for some verification steps can also be a big barrier, especially for newcomers. And in our experience, we have found that many people do not know where to start when they initiate a verification project. So our proposal intends to make us less dependent on this FAIRI and more autonomous verifiers of the data. And I will start discussing this proposal now. Actually, before presenting the solutions, I want to give you some context on how we identified the main challenges, and I will briefly highlight some experiences here that helped us understand how people experience verification projects. We also see in some slides that I will mention papers that we published to describe these experiences and its results. And their results. And then at the end of the presentation, I will share like a QR code that you can just like scan and have access to all these papers mentioned during this presentation. So different experiences allowed us to look at the verification from different perspectives. For example, we carried out a systematic literature review to understand how ontologies are used in bioinformatics and in FAIR. We also worked on a series of training workshops for new learners on FAIR and verification, and we have also carried out real-world projects focusing on health data, such as the AGPRD project. I will now focus on the main experiences that helped us identify one of the pain points, which is related to identifying verification objectives. So one of these experiences is our work as at AGPRD. I particularly worked there as a AGPRD verification steward together with other six or eight stewards. And we, in this group, works on supporting European organizations on making their patient registries fair. This group of verification stewards aims to facilitate communication between data owners and FAIR implementation experts. And in short, the role of this group is to guide and assist data producers in making good choices, let's say, regarding technologies and standards to be used to achieve this FAIR principles. In this work, we also, as you see in the paper here, we also curated and cataloged all issues identified by these organizations, and we propose specific solutions to these challenges identified by the organizations. Another example of experience with the verification is this bring your own data verification workshops, short for long name from BioD, where participants from different organizations bring their own data to the table. So, and together they experiment on how to make their data fair to fully explore the potential of the integrated data. So during this workshop, they learn about FAIR, the tools and the methods, and they generate, like by a hands-on, a real version of their integrated data to answer to new research questions in a faster and easier way. And since the first BioD, we have organized more than 25 BioDs, and I have participated in a few of this. And my honest impression is that after the workshops, participants, they seem more like enthusiastic, both about FAIR, but also about their own research, because now they know how FAIR can boost their own research. And in these experiences, the questions that we usually get the most are something like, well, where do I start? Is there like a list of tools and standards that I can use in my context? Like it feels like people want like a checklist or something like that. And we also noticed that people have difficulties in defining the scope of the verification project. Like, for example, which concepts should be in my semantic model, should be in my verified data. And we noticed that most of these questions are related to two specific verification steps: the identification of verification objectives and the semantic modeling of the data and metadata. What I mean is, most of the pain points are related to these two particular verification steps. So let's start by discussing the first one, identifying the verification objectives. While it may seem like a recent problem for verification, the problem of properly identifying verification objectives and requirements has been studied by software engineering for decades, let's say, my background. And the literature on software engineering claims that no other part of the work performed in the software lifecycle affects the final product more negatively than if objectives are described incorrectly. And for example, a modification in the objectives once the product has been delivered can cost up to 100 to 600 times higher, than requesting modification during the planning phase. And we assume a similar cost for changing verification's objectives at a later stage. So also based on this background on software engineering and reusing methodologies from this area, we propose a detailed workflow for identifying, describing, and organizing verification objectives. So we propose like giving very detailed description for a single step of verification workflow. I will not focus on our steps here for the sake of time, and also to not bore you with my presentation. But to give you an idea of the proposal and the detail level, I will explain the idea behind each phase, and then I present the detailed steps of phase 6. So here you can imagine like how these 6 phases have detailed steps for each. So the idea behind phase 1 is to prepare for preparation, let's say. So in this phase, those conducting the identification of verification objectives, that is the collaborators, as I said, they will identify and document the resources to be made fair. They will also check if the status of the organization's infrastructure, and they will also identify the roles of people involved in the verification project. They will also check if there are requirements constraining the project, such as time, budget, and other legal constraints, for example. In phase 2, the status of the resource to be made fair is analyzed to check it for instance, the data headers of the data are understandable, if the data needs to be anonymized, and etc. And similarly, the current infrastructure of the organization is analyzed to check, for example, if there is enough space to host the FAIR data, if access constraints can be put in place if needed, and etc. So if the results of this phase show any obstacle to verification, this should be addressed before continuing with the project planning. Phase 3 is based on a feedback we got from some data stewards from LUMC, from Leiden University Medical Center. So it is very common that experts on FAIR and experts on the domain of the data or of the resource being made FAIR don't communicate well because they are not aware of each other's domain. And this lack of knowledge about each other's domain also can lead to wrong expectations. For example, it's very common that, well, in some of the projects, let's say the healthcare workers consulting on verification, they expect a robust dashboard to be one of the results of the verification project. But this is not the case. Like, verification can make it possible and easier to build, but this is usually not one of the results of verification. So basically, the idea of this phase is that domain experts learn a little bit about FAIR, and FAIR experts learn a little bit about the domain, so they can communicate better. Phase 4 is my favorite one, as it focuses on making the resource to be made FAIR reusable for others. So in this phase, we start by building on the research or the business questions, which are then refined into more complex competency questions, which we already know from ontology research. So from these competency questions, we try to identify potential types of reusers of the resource to be made FAIR in the context of a particular question. In other words, we try to identify which question the reusers will have. I mean, will try to respond when using the verified resource in their own research. So this will allow us to prepare the resource for our use case, but also to others that we reuse our verified resource. For example, a patient representative will like to know the number of new cases of a certain rare disease when consulting a patient registry. So this will impact, for example, on defining the metadata to be published together with the resource, which standards to use, and so on and so forth. On phase 5, we start by defining the verification objectives. And to do so, we will elaborate on these previous competency questions in the context of each stakeholder. So, for example, how the patient representative with her question will be able to identify the patient registry, access it with the proper credentials and access level, and get her response. So these objectives are then aligned to the FAIR principles, which means we'll ask in the context of the identifying objective, how each letter of FAIR will support achieving that objective. So as you can see, we define a set of objectives or goals in the context of each kind of stakeholder that will probably reuse the FAIR resource. So finally, on phase 6, which is shown here in detailed steps, we prioritize goals and solutions. And for this, it is necessary that you define tasks that must be executed to implement the prioritized goals. After goals are prioritized and appropriate solutions are chosen, you must identify metadata that is required for executing such tasks. For instance, in order to make the patient registry findable in a repository of registries, which metadata about that registry needs to be collected. So examples will include the types of diseases about that registry, that this registry collects information about. And finally, the last 2 steps include addressing the need to adapt, rent, or acquire more infrastructure to support the FAIR project, and also identifying the required expertise that would support all goals that you prioritize. And at this point, you are expected to have your first set of goals that are mature enough to be seen as a verification plan. Of course, this will require validation with experts, some refinements, some adjustments, and so on and so forth. This method is fully described as examples in a paper that we published in the end of last year, and it was also used to improve the fairness of our ontologist catalog. This use is also described in another paper published last year. And we have also validated the method with a small group of participants in a tutorial held at the EDOC conference last year, which is more like a computer-related conference, computer science related. And we will repeat this tutorial again this year with the participants of the SWAT for HCLS conference, which will be held in Leiden in 2 weeks. So if you want to participate, I think registration is still open. There is a link in the QR code that will show in the end. So moving on, we are also working on providing guidance for the other crucial step, the semantic modeling of data and metadata. And here we are focusing on the use of ontologies. For this, we first tried to understand how ontologies and especially foundational ontologies are used in biomedical research. And one of the things we identified is that there is a lack of experiments testing the claims behind the use of foundational ontologies in bioinformatics. And given this gap, we decided to run some experiments ourselves. So first, let me just introduce the ontologist topic. It is well known in bioinformatics that ontologies play a role, an important role in data interoperability, especially. So by defining concepts in a precise way, ontologies allow humans and machines to communicate, also reducing the risk of ambiguous interpretation. Some researchers organize ontologies in different specificity levels. So foundational ontologies are defined at the highest level of generality or specificity, and they span many domains and model the very basic and general concepts and relations that make up the world, such as what is an object, what is an event, what is a parthood relation, what is a relation, and so on and so forth. So consequently, by providing a strong foundation for these very basic concepts of the world, foundational ontologies can improve the level of interoperability between other ontologies that are based on them. However, we have an hypothesis that the use of foundational ontologies in bioinformatics has not been properly tested. And to test this hypothesis about the lack of testing, we executed a systematic literature mapping on the use of foundational ontologies in biomedical research. I will not go into the full method of the literature mapping and the results here, also to not bore you, but you can check it on this paper. And in brief, our conclusions are, first, there is a lack of experimentation about the claims of using ontologies, but this does not mean that, well, the claimed advantages or the claimed disadvantages are under or overestimated. This simply indicates that there is a need for experimentation. We have also found that most ontologies are developed in an ad hoc manner, and they are poorly validated and tested. We have numbers in the paper, so you can check. And this also implies a need for new methods or to increase awareness on ontology validation and construction. So as I said, since there is a lack of experiments in our field, we decided to start with an experiment ourselves, which I will show now in the last part of this presentation. So we decided to experiment with the impact of foundational ontologies in the predictions and explanations generated by explainable AI. This experiment was actually conducted by Rosa Zwart, a master student from our group. I supervised her together with other people from our group. And we focused on explainable AI algorithms because we hypothesized that the semantics of the data can have a high impact on generating human understandable explanations. So explainable AI algorithms tackle the black box characteristic of standard AI, as usually the reasoning behind the predictions cannot be, the standard predictions cannot be understood by humans. And to do this, we build on a previous project from another master student, Pablo. So in this first project, the student attempted to identify drug candidates that could be repurposed to treat symptoms of Duchenne muscular dystrophy, which is a rare disease. And he also tried to get explanations for such predictions. So what we basically did was to extract the data model from the original project and reconstruct the model by grounding it on a foundational ontology, performing proper ontological analysis of this model. And so, yeah, grounding data on foundational ontologies is expected to improve the quality of the models given these philosophical theories embedded in foundational ontologies, let's say. And after restructuring the data, we then run the training, generation of predictions and explanations on top of the original data from Pablo, and on top of the same data restructured, we're using the new model, the new foundation ontology-based model, let's say. And then we compared both results. So this is the original model from our colleagues' work. And you can see here, for instance, that few concepts are overloaded with lots of relationships. And you can observe that we have the concepts of genes, ortholog, variant, genotype, and they are closely related to the concept of disease. This schema shows the resulting domain model from the previously mentioned steps, that is grounding this one on a foundational ontology. And I will not elaborate on all the details here, but you can observe that the model was enriched with more concepts and that these concepts are less overloaded with different relationships. And we have also validated this model with domain experts in several validation sessions. I also want to mention that we didn't include new data. In the previous model, lots of terms were overloaded, and we basically split it up here in this model in a more detailed manner. So after running the predictions and ranking the highest candidates from each knowledge graph, we got the following responses. So for the original knowledge graph, it was predicted that neratinib treats delayed speech, language development, and global developmental delay. And from the restructured knowledge graph, it was predicted that levosimendan treats arrhythmia and cardiomyopathy. We haven't managed to validate these predictions in the lab yet, but since we are dealing with AI, I attempted to ask the AI itself about these predictions, just to show you. So first, I asked Bing, this time, not ChatGPT, about the prediction on the original data. So I asked, is there any evidence that neratinib treats delayed speech? And interestingly, it responded that according to textual results, not knowledge graphs, there is some suggestion that neratinib can worsen delayed speech. And I asked a similar question about the prediction that we got from the restructured knowledge graph. I asked if there is any evidence that levosimendan treats cardiomyopathy, and it responded that there is evidence that the prediction actually can be used to treat such kind of symptoms. In terms of performance, we can see that the training curve of the model, we use the GNN model. Yeah, you can see that the training curve on the restriction graph starts with a higher score, and then there is less improvement throughout the training epochs. So if this behavior is repeated on larger data sets, it can lead to savings, for example, in time and computing power, electricity, and so on and so forth. And we also need to investigate if less improvement actually means less overfitting. And finally, it's important to note, maybe I didn't mention during the presentation, that the algorithm generates the predictions with a certain level of randomness. So we also wanted to assess the randomness. This randomness, it basically means that every time you ask for an explanation about a prediction, it can generate slightly different responses. So to assess this randomness, we run the algorithm 10 times on top of each prediction, and we compared all 10 explanations among themselves. So these pictures here show a heat map on how the predictions overlap with each other, that is, the randomness differences among these predictions. And we can observe that the overlap ratio increased when using the restructured knowledge graph as input of the prediction pipeline, which probably means less randomness in the predictions made on top of data grounded on a foundational ontology. So lots of exciting results, but so far they mean nothing. That's because we have only done this experiment with one data set. And we don't know yet if we have just been super lucky to have so many exciting results, or if our initial evidences are actually valid. So in any ways, these results point out to interesting directions for future research, and we'll replicate this experiment with other data sets and also other contexts, not only rare diseases. And well, if we manage to validate these claims about the use of foundational ontologies, we also use them as a main, let's say, artifact to build a similar method for providing very detailed guidance on semantic modeling for FAIRification. So concluding recap, we have built on different use cases to identify the most important and troublesome issues in making data fair. And in these experiences, we have also investigated how foundational ontologies can be used in biomedical research, as we also want to provide methods to facilitate the use of such ontologies. As a side effect, we found that these ontologies could have a positive impact on AI and explainable AI. We hope that the artifacts produced during this research will support research on FAIR, and especially on FAIR for rare diseases. And we hope that our methods will support our communities in making choices on tools and standards, and also sharing lessons learned with others, so to make FAIR more easier for newcomers. Throughout this presentation, I've used the words we and ours to refer to this research, because I don't think any research could be done alone. And there are some people who have worked with me and supported me along the way, and that I'm very grateful. So special thanks to the people from the LUMC Biosemantics group, the GPRD Verification Stewards, and the Semantics Cybersecurity and Services group at the University of Twente in the Netherlands. Thank you also to you for your attention, and I'm happy to answer any questions. And this is the QR code I mentioned. If you scan it, you see like a link tree with all the links to the papers and the workshops and so on and so forth.
Excellent. For all of our attendees, if you have any questions, please add them into the chat or the Q&A tab, and I will ask them on your behalf. To give them some time, I'm going to ask the first one. So
Sure.
I did not hear about FAIR at all when I was getting my degree. Didn't do much in ontology work. It was just not really aware where I did anything. Looking back on it, with it being situations like that where there's a lot of data, a lot of research that was done without considering any fair approaches to it. To verify those works, is there any indication that something will be really quick and easily applied to verification, or if this specific publication will be really difficult to make fair?
I'm not sure I got your question. Are you asking like if there is hope in the future that FAIR will be made more easy to be implemented?
In that also, more I was asking, is there like an indicator of, can you look at a paper and read the abstract and go, this can be pretty quickly, like it's not, it doesn't adhere to FAIR principles, but it could be made to work with FAIR pretty quickly? Or is there an indication for the other way where you read one and go, oh, this is just going to be a lot of work to try and verify so that it can be made more available?
Okay, yeah. You're asking like if there are evidences in the, for example, the data or the project that show how easy or how difficult verification will be.
Exactly. Yeah.
Yeah. I would say the complexity of the domain, right? I had a professor that usually used to say when people complain that, for example, ontologies are a complex artifact. And he usually says, well, ontologies are not very complex. You're just using them to solve very complex problems. So I would say the more complex the domain is, probably the more complex some verification steps will be as well. But also it also depends on how old the data is and how documented it is. For example, you have to understand the concepts in your data if you want to make it fair. Sometimes it requires a lot of effort, or sometimes like you have a very well documented data, high quality, then you can easily just apply some standards and then make it fair.
All right.
So
that makes sense.
In short, complexity of the domain and quality of data of the resource.
All right. Yeah. No. Interesting. And then the follow up. Do you think it is a monumental task to go back to old data and verify it, or do you think that is getting easier to do?
I hope it's getting easier and easier because, well, we want to make most of the data fair if possible, right? Mm-hmm. And I have a feeling that it's becoming more easy because, for example, if you look at the research on FAIR, like years ago, we had very simple tools doing just like single things, and most of the tools were like very developed in a research setting, so very how do you say that in English, test tools developed just to prove a concept and so on and so forth. And today we have companies developing software to support verification, and I hope that this more robust software will also facilitate the process.
Interesting. Is there one company or software that is your favorite that you think is better developed or better executed or even just better advertised?
I don't have a favorite, but well, now it comes to my mind for the case of, for example, patient registries, Castor. I think they're from the Netherlands, and also Mogenis, which is open source, and they usually facilitate, for example, the generation of fair data at the moment it is collected.
Okay, neat. So we have a question here. They start by saying, "Great talk. Thanks so much for presenting.
You're
I'm
welcome.
I'm curious if you speak a bit more about your use of ChatGPT to help with examining output from your models. Do you also see a role for LLMs like this to help with KG construction and or subnetworks selection for the types of analyses that you're interested in?"
Wow, this is a very good question. Thanks for this question, by the way. As you could see in the presentation, I use it very simply for just like to ask, well, what do you think about this prediction? And I'm not quite sure about my opinion about LLMs, but I don't think they will ever like fully generate the very robust knowledge graph, but they will be very useful tools to support this process. And that's one of the reasons fair data it's important, right? Like for this, for example, LLMs to work properly, they need good quality and very fair data. And I would say the better the data, the better the output. It's like a improvement cycle. You improve one side and improve the other.
Hmm. That's my PI used to always say, "Garbage in, garbage out."
Uh-huh.
Flip side of the same concept. So yep.
Yeah,
um,
exactly.
so a secondary question associated with that is they say that KGs can get pretty big. Is there a way that LLMs can be used to help reduce the search space or something similar?
Well, I'm not quite sure, but because my research or my input on the project I presented was more on the ontology side. My student was the LLM expert. And I can talk about ontologies because there is also research on how foundational ontologies can be used for summarization of complex models. And I could really envision like the two you being used together because the foundational ontologies, they also have the levels, and there are methods that use foundational ontologies to summarize detailed concepts in more complete concepts, more like overview ones.
Mhm.
And I would say like if you navigate one level above using ontologies and LLM models as support tooling, this could be done.
Okay.
Mm.
That one goes beyond my understanding, but I see some thumbs up popping from chat, so I'm going to take it that that was a good answer. um, so give everyone else a chance to get one more question in here. If you, what would you say is your next big step, your wish list project, as it were? Where would you want to go next if you could
Well,
take it anywhere?
as I said in the presentation, we have like very exciting results, but they mean nothing. And I would really like to repeat or perform like a very similar experiment with foundational ontologies in AI and XAI, but in different data sets and different contexts, just to check if we really have exciting results or it was just a matter of luck.
Okay. Now this may be just a naive question, so I apologize, but how limiting can context be? Like, if you make a discovery and find a relation or find something that is useful, can it shift from one context to another like that, or is it very context restrictive?
What do you mean by context restrictive?
Um, you just mentioned, you can find stuff in you were looking you found some neat results in that context.
Mm-hmm.
If you moved
Mm-hmm.
to a different context,
Ah,
does it translate well, or is that often a barrier?
that is not a naive question. That is a very good question.
Oh, thank you.
Um, I would expect these results I expect these results to show to be more like promising or like to
Hmm.
I mean that we could notice a bigger difference in more complex domains. I can comment on, because, for example, I didn't show the explanations, but the explanations generated from the knowledge graph were subgraphs that like try to show the path of the prediction, like why this link node prediction was performed, because, well, of these other nodes, and it tries to find a complete path.
Okay.
And we then asked other people to validate the explanations as well. So we basically like we send out like a survey with a link, and we developed a script where people like would click on this link and they get one explanation, like one prediction, one explanation, and they validate if the explanation is good or not. So they would not know if the explanation comes from the original or the restructured knowledge graph. And maybe, I don't know, like it was the way we asked, or I don't know, but we found out that the explanations from the original knowledge graph were marked as more understandable.
Okay.
But we have to investigate if being more understandable means what? Being more simple, or they have less information, or it's because they are actually more understandable, or if people, for example, are so used with those knowledge graphs, because we use public data, that when they see something different, they find it like weird. So I would say that the complexity put in an explanation also impacts its perception. And we would assume the same for the predictions and the and the performance of the algorithms.
Okay, that makes sense. So we have another question here. You mentioned using foundational ontologies, excuse me, foundational ontologies to summarize model output. Can you explain more and maybe share an example?
I actually just mentioned that because I remember a paper from Giancarlo Guisardi that uses the unified foundational ontology to like zoom in and out in very complex conceptual models. So, and I think you can also use the different let's say hierarchical levels of an ontology, right? Because sometimes you have like, imagine like in a tree, you have like the concepts, there are like leaves in the tree, and you can go back and back and back. And similarly to foundational ontologies, you have like concepts that are very high level and concepts that are more specific in the realm of the foundational ontology. And that connected together, like the foundation and the domain ontology can be used, like I imagine like a slider that you can go from one side to the other, and in the background you navigate on the hierarchy of ontologies.